Hello everyone, welcome to lecture 4 of week 6. So in this week we have been discussing about pre-training. So in the last few lectures we talked about how to pre-train transformer encoder and encoder decoder. So in this lecture we'll discuss about how to pre-train transformer decoder. Now this will be easier than the previous two pre-training models because this uses language modeling as the default pre-training framework. So we will still go through some important aspects about pre-training this and also how to use that in application, right? How to fine tune it for various applications. So these will be the concepts that we will be covering, that how do you pre-train a transformer decoder. And in decoder we will take very specific case of GPT that has been the most popular decoder, and we will talk about GPT series in general, GPT 1, 2 and 3. So how do you fine tune GPT for various NLP tasks, and then we will discuss how some very interesting aspects that came with GPT about zero shot performance and in context learning. So we'll talk about that in briefly also. So before we do that, let's try this problem based on our discussion on pre-training encoder. Fine tuning it for span based application last lecture. So what is the problem? So suppose you are using BERT for reading comprehension based question answering, and your input paragraph is this. So what you have to do, you have to find a span, start and end token from there that answers your question. So we are not giving you the question for this, for this particular problem, but you would have CLS token, then the question, then the separator, and then this paragraph, right? And this paragraph only you have to find out the start and end span of the answer. Now assume that each word is part of vocabulary, so you don't have byte pair tokens, so you can ignore the biased terms. These 6 terms are there in the paragraph, right? And this is your ground truth. Biased terms is your ground truth. Now assume that your hidden state is just 2 dimensions, so that we can actually do this problem. So what you need for fine tuning here, you need a start and an end vector. So your start vector is 1 minus 1 and end vector is minus 1 1, and you're also given the final embedding for all these 6 tokens, right? So there are various parts of this question. So if this was a sentence during training, what would be the loss for the sentence, right? So how do you compute the loss for the sentence? So you have the minus 1 minus 1 1 1 1 2 2 1 1 minus 2 2 minus 1, 6 embeddings. You have the start vector and end vector. So what you do, you compute the score s dot ti. So you compute s dot ti. So 1 minus 1 multiplied with minus 1 will give you minus 1 plus 1 0. This will give you again 0, and this will give you 1 minus 2 minus 1. This will give you 2 minus 1 1 3 3, right? So let's do it only for start vectors. You can similarly do for end vector, right? So I'm assuming this is correct. It may be so let's see. So then what will be the loss? So we know this is the ground truth start token bias. So what is the loss? It will be minus log probability. So what is the probability? E to the power 3 divided by E0 plus E0 plus E minus 1 plus E1 plus E3 plus E3. That will be the loss for the start token. Similarly, you will compute the loss for the end token, right? So that will be part A. Part B is, if this was a sentence during inference, how many spans would you have to consider, right? So how many spans do I consider? So out of 6, you can choose any 2. That will be all greater than 1 length span. So these are 15. Plus how many length 1 span? 6. So there are 21 spans. So that is part B. C is, assume that it is given that the span can have at most 2 words. what will be the output at the inference time. So that means you can have either one word span or and two word span. So let's see. So in this case, your start and end vector are negative of each other and negation of each other. So if you take E just minus S, so E dot Ti will be just minus of this. So 0, 0, 1, minus 1, minus 3, minus 3, right? So that means if you add them for a single token, like for one word token, they will be 0. So if you add them, so if you have a one word token, S dot Ti plus E dot Ti for that token will be 0. So one word tokens cannot be an answer, right? I mean, unless you don't get anything positive in this two word tokens. So then we have to consider two word tokens. So we will take, for example, this span. What is the first span? You can. So you can, the score will be 0 plus 0, 0. Then can ignore 0 plus 1. Ignore the minus 1, minus 1, minus 2. Next 1, minus 3, minus 2. Next 3, minus 3, 0, right? So the highest score is for can ignore. So this has the highest score as dot Ti plus E dot Tj, right? So this will be the answer that you will get if you can only consider at most two words. So can ignore will be your answer. Okay, so you some calculations are here for the error in part A. So now let's come to the particular topic for this lecture, that is how do you pretrain decoders. Decoder means you are going with, it's a causal decoder, so you are not looking back, you're not looking not looking at the future tokens. So you can only attend to the past tokens, right? And the natural way you can pretrain them is language models. So you take on the data on the web and pretrain them using next token prediction task. So you are given a word, you pass it through encode through this decoder, predict the next token. At pretraining time, you apply teacher forcing. So I'll use it to compute the loss. I'll compute the loss based on my ground truth and feed the ground truth token again at the next point. I'll compute the loss based on this ground truth and feed it at the next token, irrespective of which token has the highest probability, right? So that's how I pre-train this. So very simple, like in transformer decoder. I take transformer decoder and pre-train it for language modeling task on large data. So GPT was one such, one of the very first decoder pre-trained model, and that's where the name, you can say, generative pre-trained transformer, right? So it's a generative model, just a decoder based model, and it has a very similar configuration as BERT. Actually BERT came after that, so which used the same configuration. So it had 12 layers, 760 dimension hidden state, and 768 into 4, that is 3072 dimensional feed forward hidden state. Okay. Now the only reason why it had more parameters than BERT was that it was using slightly higher vocabulary than BERT. So its vocabulary was 40,000, BERT had around 31,000 or so. It was trained on book corpus, and it contains long span of contiguous text for training long distance dependency, right? So the language model was trained with very long passage of text. And then there is a whole GPT series. I'm not talking beyond GPT-3. So GPT-1 had, as we mentioned, 117 million parameters, 12 decoder layers. It can take up to 112 tokens in the context, and 768 was the dimension for the hidden layer, and they used a particular batch size of 64. Now GPT-2, you can see, was immediately on a very high level, right, 10 times. So it was 1.5 billion. We will see there had multiple versions of GPT-2. So one was 1.5 billion, 48 layers of decoder, and it could take twice the context, 1024, and hidden layer was like also roughly more than twice, and used a higher batch size. GPT-3 is like 100 times more parameters than GPT-2. So it had 117.5 billion parameters, 96 decoder layers, 2046 context tokens and 12,288 hidden layer size, right? And actually if you try, you can actually get this number of parameters using our formula, right? Remember our formula, so we can apply this formula and you can get this number of parameters. So you can apply this 12 model dimension square times number of layers, right? So layers, number of layers are 96 and this is 12,288. You can do the maths and this will give you very close to 175 billion parameters. So we'll briefly talk about this this GPT series. So GPT-2, as I mentioned, the highest model was extra large, that had 48 decoder layers of decoder, and 1600 was the model dimensionality. But they had other versions. GPT-2 small had just 12 decoder. So this was very similar to GPT-1. So 12 decoder layers and 768 model dimensionality. Then there was medium and there was large, and this is the final GPT-2 model, right? And you can see that they kept on increasing the number of layers in the decoder, and this gave better and better performance. So just a quick recap. So unlike encoder, you have a mass self attention, so you cannot attend to the future tokens in the decoder, right? So encoder had bidirectional attention. Here you have a mass self attention. Otherwise, exactly similar as encoder model. So you have mass self attention, feed forward neural network in a decoder block, and of course you have this add and normalize and other operations, and you can repeat such decoder blocks. And what it does, so like GPT-2 could process 1024 tokens, and each token will flow through its own path in decoder. So you will start from the start token and you will keep on generating embeddings at various levels until you get the final embedding. And if you are doing inference, you can just select the word based on any decoding strategy like greedy decoding, and you feed it at the next token, and you keep on generating the word until you have met some stopping criteria, right? So yeah, I mean, you feed the start token and you go through that, you get the embedding finally, and you have a linear layer that will project it to the vocabulary space and find the word with the highest probability, right? And then that word you feed at the next token, and you again go through that. Now it can attend to the previous token, right? And it can generate finally a token thing that will go in the next position. So this is the standard way decoders work. So pre-training, you compute the loss, right, and use teacher forcing. At inference time, you simply use some certain strategy for predicting the token, right? I mean, we talked about some decoding strategy, including random sampling and top P, top K, etc. So you can use any strategy for decoding. So temperature has been a very popular way of decoding, for example. Now, how do we use the pre-trained decoders, right? So if your output is sequence, it becomes a very standard choice, right? So like we are talking about dialogue, so there may be some context to the dialogue, some previous utterances between two users or system and a users that have happened. So that is your dialogue history, and then you want to generate the next dialogue, or summarization where you have document as the context and you want to summarize it. Now it's not an encoder decoder model. So like in encoder decoder model, I could have fed this to the encoder, the input to the encoder, and generate output in the decoder, right? That looks like a more standard way of doing these things, right? Summarization. You feed input in the encoder and get the output from the decoder. But how exactly do we use a decoder only model for summarization and dialogue tasks, right? So there is no way you can feed input. So the only thing you can do, you can keep on generating tokens, right? But in the decoder model also, I can give the input there. So I can say this is my input, right? I can feed the words. The only thing that will happen is that they will not be able to do bidirectional. They will not be able to do bidirectional attention, but they can still do this causal attention. They can still attend to the previous token and generate representations, right? They can generate this key value pairs that I will use when I start generating the output, right? So I can still attend to these tokens. So my output token can still attend to these. That's what I want. So in the case of encoder decoder model, whenever I'm generating the output, I can attend to all the input tokens through the cross attention, and I can also attend to the generated tokens using masked self-attention. Here also I can do the same thing. So every token that I am trying to generate can attend to all the input tokens for sure, but in the same sequence, they are in the same sequence, right? They are not, there is no cross attention. You just use masked self-attention to attend to the input, and plus whatever output you have generated, you can also attend to it through masked self-attention, right? So you can still do the same things, right? I mean, in the same sequence without making use of encoder decoder architecture, and you can do that with less number of parameters because you just have decoder here, not the encoder decoder, which needs more than double the parameters, right? And that's why this has become very popular. Like this is one example on how you can use GPT-2 for machine translation, and this we are seeing the standard fine tuning, right? So what you can do, so let's say I have some data set, training data set where I have English sentence and the French translation, and I want to fine tune GPT-2 for English to French translation. So what I will do, I'll create some, I'll have some way in which I can convert my training data into a sequence, right, into sequences. So like I can do like that. I am a student and I say a specific token that I want to translate to French, to FR. It's just a special token, and then the French translation. And I can fine tune the model using this sequence, right? I can fine tune using this sequence because a decoder model, I can compute the next word. I mean, I can compute the cross entropy loss for the next word, and I can train it. Specifically, what I can do, I can start computing the loss after I train, after I put these tokens. When I start generating this, then only I can compute the loss, right? That can be one way I can fine tune it. So I can fine tune, I can update my parameters. I give a next sentence with here, and I generate and I update my parameters, and so on. So I can fine tune my decoder using a training data set, and then you give me a new sentence once it is already fine tuned. I give a new sentence, so I feed it, I generate just all the query key value pairs for the previous words, and then with this 2FR token, I start generating the first token of my output, right? Output number 1, I feed it back and I generate the next position of the next output. So that can be one way I can use the transformer, that's the decoder model for doing translation, right? And like that you can do it for any specific generation task. You feed, you create the training data set, you templatize it in like a sequence, use that to fine tune the decoder, GPT decoder, and then you use the fine tune model for your task, right? Like summarization, so you have an article 1, all the tokens, the document, you have a specific token called summarize, and then you have the summary, right? And you can just feed this sequences into the model. You can do next, while fine tuning, you can even fine tune over everything here, next token prediction task, and at once you have fine tuned, you give a new article and the summarized token, and then you get the output, the summary, right? You can generate the summary. So it's a very nice and elegant way of using just the decoder model for doing sequence to sequence tasks, right? So this is one way this became very, very popular. Nowadays people just use decoder only models for doing nearly everything. So now you may also ask, like, what about other tasks? Like BERT was able to do classification, NLI. Can I also do all that with GPT models? And actually it's also not very difficult, right? I mean, so we saw in T5, so T5 model itself said, oh, you can do any sort of classification regression task using T5 because every problem can be seen as some generation problem, right? And that is the idea GPT also took, that right, so I can just work with a prompt, I mean just some sort of description. So you take any NLP task, you can express it in a probabilistic framework. Like why probabilistic? Because I have the token probabilities. So I always get a distribution over tokens. So as estimating the conditional distribution of output given input. So you give the input and you predict the output, right? And the input can be given in GPT as the prefix, and then you start generating the output as one after another. So output can be one token, more than one tokens. So for example, you have a reading comprehension thing. So you can say answer the question. It can all be in prompt, I mean just given as the input, then you give the document, you give the question and the answer. So like that you can fine tune the model, and then at inference time you only give up to here and generate the answer, right. So like what we saw in the previous case GPT-2, you can give all that at the inference time and let it generate tokens. That is the answer, right. You fine tune it for this task and then do inference for this task. Now how do you format inputs? Now let's take an example for natural language inference. So you have this premise: the man is in the doorway. Hypothesis: the person is near the door, and you want to know whether there is an entailment relation between premise and hypothesis. So what they did in this is the GPT-1 model. So what they did, okay, I'll use a star token, then I'll feed the premise, then a delimiter token, I'll feed the hypothesis, then I'll have an extract token, right. So they had something different. They were not just generating. They're saying, okay, I have an extract token, fine, and then you pass this through the decoder, and you get the final contextual embedding. So you have the embeddings, just like you get embeddings at the encoder, you also get embeddings at the decoder. So you have an embedding for extract, right. Now what they did, they said, okay, I'll use this final embedding for extract, right, and from there I will just try to do classification, right. This is like how BERT was using CLS token for classification. They were using the extract token for classification, right. So I have the extract token and I can classify. Now a simple question here, like why they did use the last token while BERT used the first token? And the answer is that they use the last token because they don't have bidirectional attention. So only the last token will be able to get the entire context, while BERT has bidirectional attention, so even the first token can get entire context, right. So once you have the extract representation, they apply a linear layer. I mean, so this is like very simple way of doing things, just exactly like BERT, just that you use the final token to do the readout, right. So you put everything like start, context, delimiter, hypothesis, extract as a token, right, and then you pass through transformer, you get the embedding for extract and apply a linear layer, right, and that will give you the final output. Like you may have similarity, fine, you take two text, you apply an extract token to a transformer and apply a linear layer on top of that. You may have multiple choice question, same thing can be done, right. So in the GPT-1 model, I mean this is was the one default way of using it for any particular task. So you apply extract token and now you should use it like CLS token of your BERT architecture, right. So you apply some additional interface on top of this, some linear layer, right. So linear layers were there for various tasks and you use that. Now in GPT-2 they started seeing, so the GPT family was very, very exciting. So GPT itself made a lot of noise, but GPT-2, GPT-3 they made even more noise, right. I mean, like one thing that came in with GPT-2 was some new things about zero shot and in context capability, right. So this was from that paper. So what they said, we demonstrated language models can perform downstream task in a zero shot setting. What do I mean by zero shot setting? So like I was telling about fine tuning the model for a task, but they were saying I don't need to modify the architecture, I don't need to fine tune it, I just give the task and the architecture is good enough to perform it without any further fine tuning, right. So for example, to summarize what they did, so they add the text and they have this TLDR token after the article, and then they start generating, right. I mean you give the input and let it generate, and they just generate 100 tokens, and that was a good enough summary, right. That's what they found. They also saw it for translation experiments, and what they did, so they took some example pairs of format English sentence is equal to French sentence, yes, and then so this is like in context learning. I'll talk about it more when we come to the GPT-3. But what they said, okay, I will just create a format where I'll give some examples like English sentence equal to French sentence, right, and I'll give many examples in the input, right, not fine tuning, just in the input, and then a final prompt will be an English sentence equal to, and then you just start generating, right. So you can have English sentence 1 equal to French sentence 1, the first one example pair of translation, then you have English sentence 2 equal to French sentence 2. So like that you give some examples and then finally you have an English sentence input, and you want the output for that. So you just give this as your input, entire thing as your input to your GPT-2 model, and let it generate tokens from here, one after another, autoregressively. And they found that with this, just use greedy decoding and use the first generated sentence as a translation, and that was able to perform quite well, right? So this was an in-context learning thing. So where you give some example of the task in context, you don't train the model at all. I mean, you don't fine tune the model. So, and they also did it for question answer pairs, and then if you want short answer type, you give accordingly some short answer examples in your in context examples, and given a question was able to do short answers, right? So this was just the beginning of the zero shot in context behavior that we saw in GPT-2, right? So this was like what they showed. So as you increase the model size, the zero shot capability actually increases, right? So without any explicit supervision in zero shot setting, so you can see that if you increase the number of parameters, right? 1.5 billion was the largest model of GPT-2, so 117M was the smallest, and you see the zero shot performance keeps on increasing, and this was very close to one of the best models that time, DRQA, right? So this reading comprehension. Translation, it was able to do better than many models. So again, summarization and question answering. So you are able to do better and better in zero shot, right? So like in this was specifically the one that they pointed out, that it could reach 55 F1 on COCA data set just by zero shot performance on 1.5 billion transformer. Now GPT-3 was a cultural movement. I mean, so the interesting thing with GPT-3 was, with GPT-2 we could still do fine tuning. GPT-3 was only available when it was launched in a prompting setup, that you cannot fine tune the parameters. You can just play by giving zero shot examples. Like question, you give a question, get the answer. You give some example inputs of your task and let it generate the output for a new task, right? So you could only play with it in an in context learning setup. So what this showed, that you can scale up the language model, and it helps it to achieve some task agnostic few shot performance. Sometimes it was reaching competitive performance with the state of the art fine tuning approaches, and that was what was shocking. So just by using this few shot in context learning, you could do as well as the fine tuning on data sets, right? So this came with 175 billion parameters, right? And this was very important. They applied without any gradient updates or fine tuning, and many data sets, including translation, question answering, and closed tasks, and tasks where they require on-the-fly reasoning, domain adaptation, right? So it was doing very, very well, right? So we will talk about this in more detail when we talk about prompting frameworks. But I mean, just to give you a terminology of this, so we call in context learning whenever we have a language model that is pre-trained, but we freeze its parameters, right? And the only way we reason it by giving prompt text. And what is prompt text is nothing but, so you have a frozen GPT model, and you give the input to the decoder, right? So you give some W1, Wn, some input to the decoder, from which it can generate its query key value, and then from the last input you start now generating your tokens. So output 1, you feed it, get output 2, feed it, right? So that's all is the prompting. So you feed some input, it does its own thing. I mean, you will convert it to embeddings, it will convert into query key values, get the final embeddings also. It will do everything with that, right? So you just feed this is the prompt, but you don't tune the model, you don't change its parameters. But now when it starts generating, it makes use of all of these tokens, right? Whatever you have given as input, it makes use of that, and it starts generating conditioning on this, right? So this is the in context learning. So specifically we talk about two things, few shot and zero shot in context learning. So in few shot in context learning, what will happen, the prompt you have given will include some examples of the task. Like we said, you will give an English sentence and the corresponding French sentence, another English sentence and French sentence, then you will end with an English sentence and let the model generate a French sentence as an output, right? So you will have examples of the intended behavior that you want it to actually exhibit. And I mean, this is one hypothesis, that you have not seen such examples in the training. but we cannot verify this, right? So few shot is also used. Sometimes few shot terminology is used in supervised learning also, when you are actually fine tuning with whatever training with few examples, right? So when we are saying few shot in context learning, we are meaning we are giving some examples in context in the prompt. We are not fine tuning it, right? Similarly, zero shot in context learning means you are not giving any example of the task, right? So you have no example of the intended behavior, but you can have some instruction that like translate from English to French, and you can give other things like you should not use certain words and so on. You can give some instructions, but you will not give any examples of the behavior. Like how do you do this formatting and all? That's a whole prompt engineering thing, right? And we will maybe spend a little bit time in the 9th week. So, but yeah, this is allowed. So you can do this formatting of instructions as you want, and then you see if it works, right? So GPT-3 model, that was like 175 billion model, 100 times more than the GPT-2 model. So it showed that you can do zero shot performance, one shot and few shot, right? All in context learning. So while in fine tuning, what you would do, you will give input and output, right? And you will have some loss function. Using the loss function, you will update your parameters, right? You will have some gradient update. And this gradient update is missing from here. There is no gradient update. Whatever you have to show, you have to tell, you have to give a description, and you may give some example, zero shot, one shot, few shot, some examples. And it is learning to learn. It is given these examples, it learns what kind of format I have to predict for the output, and it does the few shot in context learning. Okay. So for GPT-3, for example, fine tuning was not available. So the only way we could interface with GPT-3 was prompting. So like I want to do classification, right? Sentiment analysis. So my input is I love this movie. So I have to have some way in which I can put it as a prompt. So I will say, okay, template will be X is the input, and then I'll put something that will say, okay, overall it was, right? So then it can be positive, negative, and so on, right? Fantastic. So G is what I want. So X is the input sentence, and this is like what I am giving, overall it was, and G is what I am looking for, what this model give. So something like this is what I'll prompt. I love this movie is the sentence for which you want to know the sentiment, and then you have your own thing, overall it was, and G, and you will get what is the generation of the model. Like the model can generate fantastic, right? So then you may have to have some way of converting this fantastic to the classes that you have. Maybe you have some positive and negative class. So whatever token that generated, you should have some way in converting it to the positive and negative sentiment and so on. Right? So this is again a very interesting aspect of learning with prompts. Okay. So we'll talk about this briefly in the 9th week. Okay. So yeah, for this particular lecture, you may go through this book, Large Language Models, a deep dive, specifically chapter 2. This also gives a lot of other pre-training objectives that people use in general. Okay. So in the next lecture, we will talk more about how do you even adapt these pre-training models for domain applications or languages, right? So we'll see that in the next lecture. Thank you.